gentlemen. My name is Paul Bukorny. As Chairman said, I'm from the same institute, and also I am a PhD student still at the Brno University of Technology. Today I would like to speak about the influence of variable stress ratio on residual fatigue lifetime of radial axles. Here you can see the content of my presentation. So firstly, I will speak about the radial axle loading. Then I will speak about the operation stress ratio of radial axles, effect of variable stress ratio on residual fatigue lifetime, and finally I will conclude my talk. So, in our work, we calculate residual fatigue lifetime of radial axles based on damage tolerance approach. In this approach, we consider initial crack, and the crack is considered at the position where potential crack causes the shortest residual fatigue lifetime. This place is situated at the notch near to press-fitted wheel, where is the stress concentration, and additionally there is also the additional load due to the press-fitted wheel. We assume that crack grows perpendicularly to radial axle axis due to the fact that fatigue crack grows perpendicularly to maximal principal stress, and in the case of radial axles, the maximal principal stress is almost the same as the longitudinal stress. Our considered crack is semi-elliptical due to the fact that semi-elliptical shape is easy to express by mathematics, and also it's in the relatively good agreement with the observation of real fatigue crack fronts. Also, it's necessary to mention that we assume the changing ratio between semi-axis A and B during the fatigue crack propagation rate. Based on numerical calculation by finite element method and based on this equation, we can determine the stress intensity factors, and stress intensity factors are determined for two basic kinds of the loading. First kind of loading is by the weight of the train, which causes dominant bending loading. And second one, as I mentioned, is loading due to the press-fitted wheel. Here you can see the calculated stress intensity factors for both mentioned kind of loading. So with the red, the load due to the press-fitted wheel, and in the blue, the load caused by the weight of the train. And the total stress intensity factor is given by this relationship. But the problem is that the bending moment is not constant, because the loading due to the weight of the train maybe corresponds just to the right of the train on the straight track. But the train also goes to the curved track over switches, over crossovers. We have fully loaded train, unloaded train, etc. So then we have variable amplitude loading, and variability could be described by the load spectrum, especially by the dynamic coefficient, which corresponds to the multiple of static load. So then we have maximum values in the load spectrum, which corresponds approximately to 3 times higher load amplitudes than in the case when we have loaded the axle just by the weight of the train. So then the total maximal stress intensity factor is given by stress intensity factor caused by the press fit plus stress intensity factor caused by the weight of the train multiplied by dynamic coefficient K. When we have non-zero mean stress due to the fact that we have influence of the press-fitted wheel, we have slightly higher mean stress, and also when we have variable amplitude loading, then we have also variable stress ratio due to the fact that we have non-zero mean stress and variable amplitude loading. Also, it's variable stress ratio. And the question is, how huge is the effect of the variable stress ratio during the loading operation on calculated residual fatigue lifetime? The critical part of the wall residual lifetime is given by the crack growth from 1 millimeter up to, let's say, 55 millimeters. And you can see that for various crack lengths and various load levels in the load spectrum, we can reach low amplitudes since approximately -1 up to stress ratio approximately 0.18. So the stress ratio could be in this range. And based on this calculation, we carry out the measurement of particle propagation rate independent from the stress intensity factor for 3 different decay curves, which were measured over 3 different stress ratios. Based on calculations, we measured particle propagation for the stress ratio -1, -0.5, and also for 0.1. This measurement was carried out on middle bench specimen, as you can see here. And now we should calculate, based on this data, the residual fatigue lifetime. And I show you 2 approaches. The first approach is when we consider the effect of the stress ratio. This effect could be described by the original NASGRO description, where the stress intensity, where the stress ratio is included in the denominator in this part of the equation. And if we take into account this whole part, then we have so-called effective stress intensity factor range. And if we apply this for all measured decay curves, then we see that each measured decay curves fits each other. So it's nice. But for material parameters in the original NASGRO description, we need at least 2 decay curves, which were determined for 2 different stress ratios. Second approach is when we do not take into account the effect of the stress ratios, and we work just with the maximal stress intensity factor. In this approach, we can just calculate with the 1 decay curve, which was determined for the stress ratio -1. Due to the consideration, then if we take into account just the maximal value of the stress intensity factor, and we take into account just the data of stress ratio -1, in each case, if we calculate the maximal value by this equation, we assume the higher amplitude than is in the real case. So if we take into account just the data for stress ratio -1, we also assume some imaginary part of a cycle which is not in the reality. So then, if we take just the V key max instead of delta K effective, we will obtain quite similar trend as in the previous case. And you can see that if we use the material data which were measured on the lowest operation stress ratio, in our case -1, then we will obtain conservative results, because as you see in the linear area, the data measured for stress ratio -1 creates envelope of the other 2 measured decay curves. So then, for determination of residual fatigue lifetime, we can use just the 1 measured decay curve. So this is advantage, but we neglect the stress ratio. But as I said, in this case, we assume some imaginary part, so results should be conservative. Here, you can see the results of calculated residual fatigue lifetimes in so-called load blocks, where load blocks corresponds to certain amount of the train distance. And you can see the residual fatigue lifetimes calculated for different initial train lengths from 1.5 millimeters up to 5 millimeters. And you can see that in the case when we take into account the stress ratio effect, we will obtain approximately 20% higher residual fatigue lifetime than in the case when we neglect the stress ratio and we work just with the material data which were determined for the stress ratio -1. So let me conclude my talk. The work was focused on determination of residual fatigue lifetime based on damage tolerance approach. I was focused on the effect of variable stress ratio during the loading on calculated residual fatigue lifetime. And I showed you that if we use the NASGRO in so-called key max form, and we use the data which were measured for the lowest stress ratio, which is in the operation, in our case, -1, then the result will be conservative and approximately will be conservative about 20%. So then it depends on you. If it's necessary to take into account the stress ratio, but you need PK curves which were measured at least at two different stress ratios to determine the material parameters of original NASGRO. Or if 20% lower residual fatigue lifetime indicates that you neglect the stress ratio is enough for your estimation. And also you know that in this brief calculation you are sure that your results are conservative. So that's all. Thank you for your kind attention.